Okay, so this is proof of work. To implement a distributed timestamp server on a peer-to-peer basis, we will need to use a proof of work system similar to Adam Back's Hashcash rather than newspaper or Usenet post. So the problem with a timestamp server is generally it's centralized, okay? It's a central server. So the way we make this time server distributed, right, meaning we spread it to everyone rather than just one entity, is by using something similar to Adam Back's Hashcash. Alright, so this way we don't need to print anything onto newspapers or Usenet posts. The proof of work involves scanning for a value that when hashed, such as with a SHA-256 or SHA-256 algorithm, the hash begins with a number of 0 bits. So to simplify this technical part, here's what it's saying. Proof of work basically involves finding a number of zeros associated with our unique fingerprint that we take for each block, okay? This number is what I'm going to call a magic number. It helps us make the lock for the block, okay? This is the magic thing. It's the magic behind the blockchain and how it gets locked. Finding the next magic number, okay, requires the computer to put in some of its brain power and work it out. So think of it as like a puzzle that the computer has to solve, right? It's looking for this magic number that solves this puzzle for this block. It helps to think of it as using the unique fingerprint to find a rare number, kind of like finding a rare Pokemon. Then we use this Pokemon/number to protect/lock the block. So once you find this, you can protect the lock or the block with it. The average work required is exponential in the number of 0 bits required and can be verified by executing a single hash. So what he's saying here is basically, in order to find this number, right, this magic number, it requires a lot of computational power. But once you find it, it's pretty easy to verify, all right? This is what miners do, basically. They take the unique fingerprint of a group of transactions and let their computers mine, or rather work to find this magic number to lock the block with. For our timestamp network, we implement the proof of work by incrementing a nonce in the block until a value is found that gives the block's hash the required 0 bits. So this is the way I understand what nonces are in my head right now. I understand the technical part of it a little bit more, but it's harder for me to put it into words. So here's what I understand. Sometimes the computer finds something close to the magic number, but not the magic number itself, okay? So we add a random number that can only be used once, which is called a nonce. The computer uses this number to see, okay, is this the number? Because sometimes it gets very, very close. So it uses the nonce to verify whether it's the number or not, without throwing away all the transactions, if that makes any sense. So the computer uses this number to calculate the current magic number, but it can be only used once. So yeah, that's how it kind of works. Once the computer effort has been expanded to make it satisfy the proof of work, the block cannot be changed without redoing the work. So after the computer CPU has done the work and basically found the magic number in Pokemon, the block cannot be changed without redoing the work. Think of it as like locking the block with this lock that was found by the miners using this magic number, basically. So it's kind of like, think of it in terms of Pokemon too. So think of it as like you found the magic Pokemon that goes with the block, all right? And the Pokemon protects the block. It's going to take a lot of work for somebody to put rare Pokemon back to where you found it, okay? That's kind of how it works. But it's easier for everybody to think of it as, or people who are beginning, think of it as, locking the block, okay? All right, cool. As later blocks are chained after it, the work to change the block would include redoing all the blocks before it. What he's saying is, so as later blocks are chained/locked after this block, in order to mess with this block and all of its transaction, basically, the person or persons would need to unlock all the blocks that came after. But remember, you're not necessarily unlocking anything, you're undoing all the work. You're not really undoing, you're actually redoing the work. You're trying to break the lock, which necessarily means you have to work on breaking the lock. So let me give you an example, okay? So for example, if this is block 34 and somebody just mined block 35, your block 34 is protected by its own lock and the lock of block 35, as somebody would have to first unlock or break the lock of block 35, then come after yours. If numbers confuse you, no worries. let me give it to you in alphabet form. You just mined block S. Okay, block S is protected by its own lock. Then, as later blocks are added, say T, U, and V, your block is protected by their locks. The attacker must unlock and slash basically destroy the lock of T, U, and V first before coming after yours. But the way they do it is in chronological order, basically. So they would go from V, try to break its lock, then go to U, break its lock, and then T and its lock. So it takes work to do this. So the more of these things that are added after yours, your block S, the better off yours is, because you don't need to. Like, yours is not only locked by itself, but all the other locks are basically preventing somebody else from coming in and, like, attacking your block first. So here's a diagram by Satoshi Nakamoto. Think of this as block S, and this is T, okay? Look at this. This is the previous hash. Think of the previous hash as the previous lock that is used. So, you know what? It'll be easier to understand. So this is T, and this is S. We'll actually put it in there. So this is S, and this is T, okay? Cool. So we can see that block T carries the previous block. Basically, previous hash of block, previous hash. The previous hash is like the previous lock, if you will. So it carries the lock of block S, and carries its own nonce and its own transactions. And it uses this hash, obviously the transactions and the nonce, to calculate its own lock. So block S is carrying the lock of block R before it, its own transactions, and the miners are calculating its own unique lock here. So each block is locked by the previous one, and it creates basically a blockchain, but it's more of a lock chain that has transactions added per block, if that makes any sense. So what this diagram is saying is that each block carries the hash of the previous block. Remember, the cat prop hints, each block carries the unique fingerprint of the cats before it, and the miners use this previous fingerprint of the cat to find the block's magic number, which is used to lock the block. So an easier way to think of it is, you carry the previous lock, and you use your transactions and your nonce value to calculate your magic number to lock your block. Alright, cool. So let's go on to the next one. The proof of work also solves the problem of determining representation and majority decision making. So proof of work also solves the problem of showing who voted for what. Basically, proof of work, I apparently spelled this wrong. Basically, proof of work shows what the majority voted for. If the majority are based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs, which are not hard to do, by the way. So he's saying, if we gave one vote per one internet address, a person can easily add multiple addresses and control the network and take it over, which is not what you want. Proof of work is essentially one CPU, one vote. So proof of work is basically one CPU, central processing unit. It's your computer's brain, basically. Apparently I'm spelling basically wrong. So it's saying basically it's one computer, one vote, okay? Or one CPU, one vote. So there you go. The majority of the decision is represented by the longest chain, which has the greatest proof of work effort invested in it. So we can see that the longest chain represents the majority because it takes the highest number of computers to create this chain. If a majority of computer power is controlled by honest nodes, the honest chain will grow the fastest and outpace any competing chains. See, if the majority of good and honest computers are working towards creating the longest chain, they will obviously kill any other chain forming that are probably being formed by malicious and or bad actors. To modify a pass block, an attacker would have to redo the proof of work of the block and all blocks after it, and then catch up and surpass the work of the honest nodes. So if somebody were to attack the blockchain, they would have to redo the work of the honest computers, right? Starting at whatever the recent block is. Say the recent block was at V, and then they would have to catch up where the honest nodes are. So the honest nodes are at Z, block Z, Then they would have to beat the honest nodes and then do block, A1. So think of it as like unlocking a chain of locks. Instead of unlocking, it's more like breaking a chain of locks. There are honest people always adding locks to the chain. You have to unlock each lock, and by the time you do this, more locks would be added such that you'd have to catch up to new locks and then go faster than the honest people who are just building the chain of locks to, protect their own transactions and, help everybody else out. Make sense? Okay, cool. We will show later that the probability of a slow attacker catching up diminishes exponentially as subsequent blocks are added. The math on this is ridiculous. It was very fun to learn about Poisson distribution and all the other distribution methods. The random walk was really cool to understand. Okay, so he's saying here is, we can show you mathematically that there are more locks as there are more locks in the chain, the harder it is for any attacker to unlock it. To compensate for increasing hardware speed and varying interest in running nodes over time, proof of work difficulty is determined by moving average, targeting an average number of blocks per hour. So what he's saying here is, remember that computer is looking to find the magic number that will lock in the block or lock a block. Well, see, every computer has like different power levels, right? Different types of CPUs and all that. Some can go Super Saiyan, some can't. Over time, this is a problem because it means things can get wonky. So the network automatically sets the difficulty of finding this magic number. If they're generated too fast, the difficulty increases. So if the blocks are generated too slow, the difficulty of this number decreases. If the blocks are generated too fast, the difficulty increases. Okay. And now we're on networks. So let's do networks.